This is part 2 of section 8.3. We are going to start using our properties to simplify radicals that are not exact, okay? The first thing I'm going to do, I mentioned earlier that we're going to use prime factorization to do these. I'm going to rework this problem in a second using that, but I want to show you what's actually going on, okay? By simply using the properties, I'm going to simplify this. Now what I'm going to use is this property right here. I'm going to create something like this where I have two things multiplied together, and then I'm going to split it up into two radicals. So what I'm going to do is I'm going to rewrite the square root of 18 as the square root of 9 times 2. 9 times 2 is 18. It's true. Now using the property we're talking about, I can take this and split it up into the square root of 9 times the square root of 2. The square root of 9, we know that. It's exact. It's 3. So this is 3 times the square root of 2. And normally we don't write the dot. It's understood. And we write 3 square root of 2. Obviously not a 3. Okay. If we use our calculators here and we do the square root of 18, it will simplify it for us. This is a smaller one. Okay. Now there's a huge disadvantage to using this. You may be wondering why I chose 9 and 2 instead of 3 and 6. And that's because 9 is a perfect square, 3 isn't a perfect square, neither is 6. So the problem with doing it this way is not only do you have to find a way to break it up that has a perfect square, you need to find the largest perfect square. And that's not so bad when you're dealing with small numbers that we're pretty comfortable with. But if you start dealing with larger numbers, it can get really, really difficult. So the method I'm going to show you takes more paper, and obviously if you see this immediately, go with it, okay? But that's probably not going to happen very often, at least not until you have a lot of practice with this, okay? So I'm going to rework this problem. I'm going to use prime factorizations of 18. Now I'm going to my separate sheet of paper here so I can do these neatly, okay? I'm going to find the prime factorization of 18. Now, one method of doing this was the factor tree, and I'll write that down right here. We do the factor tree, and you say, okay, I just need two things that multiply to 18. Let's do 3 and 6, since that's not the one we did earlier. Okay? I look at this 3. 3 is a prime number. Now, to help myself when I use a factor tree, I'm going to circle it, because sometimes factor trees get really big, and you can miss some of your dead ends. 6 is not a prime, so I'm going to break this down further. It is 2 times 3, and these are both prime numbers. Eventually, you will hit dead ends everywhere, and you will get your prime factorization. It does not matter what order you start breaking things down in. You will end up with the same numbers on the outside, perhaps in a different order, but you will end up with exactly the same thing. Okay? So using the prime factorization, 18 is 2 times 3 times 3. Okay? Now, what I found is that the prime factorization, the factor tree, is not very useful when we're doing these. It's hard to reuse, they get very big, and you end up repeating a lot of work. So instead of using the factor tree, I use repeated division. And what you want to do with repeated division is, right here we broke it up using a 6. I would not want to use 6 here, because I want to find a prime number. It does not matter what prime. I want to find a prime number that divides evenly into 18. Now, since it's an even number, I tend to start with a 2, okay? Because if it's even, it's divisible by 2. So 2 divided into 18 is a 9. This is kind of like an upside down division, okay? Now we want to repeat. I want to find a prime number that divides evenly into 9. I personally have a tendency to stick with a number until it doesn't work anymore. 2 does not work again, so I find some other number that works. And a 3 works, and then you have a 3. Eventually, you will end up with primes all along the outside, just like we ended up with dead ends all along here. You can see that we have exactly the same numbers. Okay? Now, I know this is a lot of explanation for this, and you might think the other method is quicker, but it's generally not. What we're going to look for here is, since our index is 2, since we're talking about a square root, we're going to be looking for pairs. If this were a cube root, I'd be looking for 3 of a kind. If it were a 5th root, I'd be looking for 5 of a kind. Here I have a pair of 3s, okay? If you have a pair, it's going to move to the outside of the radical, and you write it down once. Remember, our answer to this is 3 times the square root of 2. I have a pair of 3s, a 3 moves to the outside. This 2 did not have a pair, it did not have a partner, it is stuck on the inside. Okay, so that's basically how we're going to work these. If we're having a square root, we're looking for 2 of a kind to move to the outside. And anything that does not have enough to move to the outside is stuck on the inside. Okay, so that was a fairly simple one. Let's try negative square root of 48. A negative on the outside is always okay. Your answer is going to be negative. Okay, now I want to do a prime factorization of 48 and see what I get. Okay, 48 is an even number, so it is divisible by 2, and that gives me 24. And I keep going. 24 is also an even number, so it is divisible by 2 to give me a 12. 12 is divisible by 2 again, leaving me with a 6. And then 6 is 2 times 3. Now I could have divided any of these by 3 at any time. I would have had different numbers show up in here, but I would still have 4 2s and a 3 on the outside. Okay, so we are looking for pairs. I have a pair of 2s here, so it's going to move out. And I have another pair of 2s. So what do we do when we have more than one thing move to the outside? So a 2 is going to move out here, a 2 is going to move out here. To find out what moves out the whole on the whole, we multiply those together. So I have 2 times 2, which is 4. And on the inside, I had a 3 that never had a partner. So this is the square root of 3. Negative 4 times the square root of 3. Let's use our calculators to see if we got this right. If I can get this so it doesn't have a glare on it. Okay, here. So negative square root of 48 is negative 4 times the square root of 3. So that's correct. Okay, now like I was saying, we can use our calculators to check a square root, but they do not check any other index. So this is where we really need to know how to do this by hand, okay? I need to simplify the cube root of negative 250. First of all, I have a negative on the inside, so I need to ask myself if that's legal. This is an odd index root, so this is okay. It just means our answer is going to be a negative. If this had been an even index, this would not work. Okay, so I need to find a prime factorization of 250. All right, 250 is an even number, so it is divisible by 2. And that gives me 125. Now this is no longer divisible by 2. It ends in a 5 though, so that tells me it's divisible by 5. If I divide this by a 5, I get 25. And if I divide that by 5 again, I get 5. Okay, so the prime factorization of 250 is 2 times 5 times 5 times 5. Now this is a cube root we're looking for, so I'm looking for 3 of a kind to get to move outside. Here, I have 3 5s, so a 5 is going to move to the outside. This 2 did not have 3 of a kind, so it is stuck on the inside. So this answer, I'm going to have negative 5 times the cube root of 2. Okay, it's a cube root here, it stays a cube root here. Okay, so let's find negative 4th root of 1,250. Okay, I have a negative on the outside, which is always okay. You just move the negative over. Now I need to find the 4th root of 1250, so I need a prime factorization of 1250. Okay, 1250 is divisible by 2. And when I divide that by 2, I get 625, which is no longer divisible by 2. But it ends in a 5, so I know I can divide it by 5. And that will give me 125. Now look, I already have 125 here. I have the prime factorization of 125. All I have to do is to cover up the top of that. So this is where things get to be reused. So I have it here. I don't have to think about it anymore. I can just recopy this over here. Okay, so this is 5, 25, 5, and 5. So anytime we need a prime factorization, we should come back to our neatly done sheet of paper and see if that number is somewhere on here. If I need to find the prime factorization of 625, all I have to do is to cover up this, and I've got it. This is what I mean by things being reusable. After we do several of these, a number you're looking for, there's a good chance it appears somewhere, and you can use the work you've already done. Okay, now this is a fourth root, so I'm looking for 4 of a kind. I have 4 5s right here. So the 5 is going to move on the outside, and I have a 2 left over. So this is 5 times the 4th root of 2. Notice how similar these two are? The difference is the index.